Okay, this is the second lecture for combinational circuit design. So lecture 23, and let's go to the review of our previous lecture, lecture 22. So lecture 22, we have talk about the static CMOS. So static CMOS is the one we have studied up to now. In entire this semester, we have studied the static CMOS logic gates. Point is sizing. By sizing transistors, especially in its N MOSFET and P MOSFET, we can separately control the falling edge and rising edges propagation delay. Of course, but the lesson was if you get a benefit for a single edge, and it always comes with a cost for the opposite edge. So yes, so if you are especially interested with some edges, then you can try to size it, but usually it is not a general strategy to size too heavily outside the nominal values. Okay, so now let's go to the circuit families. So in this section, so circuit families, today we will continue to the discussion about other circuit families and non-static CMOS ones. But before starting today's lecture, I wanted to stress that actually static CMOS should be the choice for your circuit family. So if you have sufficient reason to justify your use of other circuit family, then only that case you can use other one. So in many cases, in almost all cases, static CMOS should be your choice. Okay. So especially it is related with its robustness. Robustness can be expressed in many different ways, but in nutshell, it simply means that if you make or design a certain circuit, then with a certain variation in time, manner, or some die to die. So in many cases, at least you should be able to believe that your circuit works properly. So in that sense, robustness is quite important. So it seems to be quite a general description, but the static CMOS provides you the most robust design, and for other ones, sometimes it seems to be quite attractive, but many times it lacks robustness. Okay, so the first family we will study in this today's lecture is pseudo NMOS. What is pseudo NMOS? So the name comes from the one like this. Here we have NMOS. So in this inverter case, and if you attend the microelectronics course, the first circuit you learn related with an amplifier or other kinds of CMOS logic or MOS logic is just N MOSFET with the resistive load. So this is the simplest circuit we learn in microelectronics course with MOS device. So in this case, we have learned that this circuit can work as an amplifier. If you change the input voltage a little bit, then that is magnified and amplified. So actually it is not in this way, the opposite way, but you know that if you have a small signal change in your gate voltage, and that is mapped onto the small change of your drain current. That relationship is given by just transconductance Gm, and you know that here we have VDD and the voltage reduction is given by, so this output voltage V out is simply given by VDD minus load times so drain current. And you know that in this case, by applying the small signal additional voltage Vg, so increase of drain current is simply given by Gm multiplied by Vg. So what we can say is change of output voltage is simply given by minus RL times the small change of drain current, that is given by GMVG. So when we just collect them all, we have a factor like minus GMRL times VZ as a function, as an expression for output voltage. So now we can consider some quantity, a ratio between the output voltage fluctuation and input voltage fluctuation, that is given as minus Gm times RL. This is called as a voltage gain of this amplifier. If we have sufficiently high resistive load and sufficiently high transconductance, then their product will become larger than 1. Of course, in its absolute sense, then we can say that that is working as an amplifier. So that was the ones studied in our microelectronic course, especially when we consider amplifier. This is a common so-called common source amplifier. Okay, then of course that is not the digital circuit, but it is related with the analog one. But with the same circuitry, we can try to use it as an inverter. So for example, since now all of you understand this inverter circuit, then we can easily apply this way. If we multiply or apply just 0 volt, then this MOSFET is turned off. In the case of our CMOS implementation, there we have highly driven PMOSFET. So this highly driven PMOSFET just drive our output voltage to VDD. In this case, unfortunately, we don't have such kind of a powerful pull-up network. However, still, it has a certain conductivity between our output node and VDD. So since this pull-down network is completely turned off, so we can believe that eventually it will approach it to VDD value. So this is the case. Of course, in the case when we apply VDD into our MOS gate voltage, this one, then it is the same as before. So in this case, our fully turned on MOSFET will drive this output voltage down to the ground. The only difference is in this case, when gate voltage is VDD, then in the case of our PMOSFET pull-up network was completely shut down because we have applied 0 gate to source voltage to our PMOSFET. But unfortunately, in this NMOSFET implementation, NMOSFET only implementation, here still we have RL. So the point is, in this case, now we have transistor fully turned on. It tried to drive the output voltage into ground. However, there is a certain counterbalancing reaction like RL. Also, it tried to charge this V out voltage using this VDD and difference between this one. So if that is really successful, let's say that our MOSFET is really powerful, then what will happen? Then eventually our voltage will be close to zero. So because this inverse of 1 over RL is not as strong as this MOSFET, then eventually this MOSFET will win. Then we have still certain current like VDD minus V out, but that is quite close to zero, divided by RL. This amount of current conduction will happen even when we have really small output by action of large input voltage. So this one really implements that this circuit with resistor will give you the static DC current. That was already studied in our microelectronics course. So now let's go to this, come back to our course. So in our course, we cannot easily assume the existence of a resistor. So resistor is not that easily available to us. So it's not. Then how about using just PMOSFET? But PMOSFET is just fully turned on here. So now this PMOSFET has certain strengths in its current conduction. Then it can be used as just a resistive load. So that is the reason why in this pseudo NMOS circuit, here we have NMOS and here we have PMOS. Yes, actually it is built on the CMOS technology. Both of MOSFET and PMOSFETs are used. However, in this case, PMOSFET is no longer used as just an active transistor. It is used as just a resistive load. That's all. So the reason we adopt this kind of thing is, so you know that PMOSFET is not as powerful as MOSFET, and in terms of speed, we wanted to avoid the use of this PMOSFET. So that's the reason why we just use it as resistive load. But you know that the biggest problem of this kind of approach is, once again, static power consumption. We are really power hungry in these days, and actually this power consumption was the reason why NMOS only or PMOS only technologies has been extinct. So this pseudo NMOS type approach is just to come back to the past, and this static DC current is revived. So this is not that good for power consumption, but anyway, it is good for its propagation delay. And please note that, of course, once again, when we have low input, when Vg equal to 0, then it is certain that our output voltage becomes VDD. Good. However, if we have input equal to VDD, then both of our pull down network and pull up network are alive and they are fighting each other. So if we have relatively powerful pull down network, then what will happen? The output voltage will go down. And let's say that if our pull up network and pull down network are comparable in its driving capability, then what will happen? In this case, we will have certain output voltage in between VDD and 0. So you know that if you have this kind of thing, the voltage transfer curve starting from this VDD and ends at this intermediate value, can you recognize it as a voltage transfer curve on inverter? Actually, it is really difficult to say so. So, for example, this guy, for this curve, you can say that yes, certainly it is a voltage transfer curve of an inverter. However, if we have this kind of thing, then that would be very difficult for, say, that of inverter voltage transfer curve. Okay, so therefore, it is certain that we have to have a weak, relative weak P MOSFET. If we introduce two powerful P MOSFET, actually it is just deviated from conventional inverter voltage transfer curve. So we have to have lower strength of P MOSFET, and that is also good for my cases. Okay. So in the textbook, the author suggest just a relative strength of a quarter. So compared with this N MOSFET driving capability, try to make it just 1/4 output. So now, well, anyway, let's try to consider this inverter design. Okay, now we assume that P MOSFET is 4 times weaker in terms of driving capability than, oh sorry about that here, N is missing here, than N MOSFET. Then that is the suggested inverter design, but you can see that the ratio of your N MOSFET and P MOSFET, or the size of N MOSFET P MOSFET, seems to be quite strong or quite strange. So we have 4/3, 2/3. Why do we select it in that way? Of course, you can see that one thing quite easily. So the ratio shown here, 2/3 and 4/3, is related with our assumption, like our N MOSFET should be 4 times powerful than our P MOSFET. So you know, since it has roughly just half mobility than that one, so let's say that our N MOSFET will conduct, for example, 4/3 I, and in this case for P MOSFET we will have just 1/3 of I. So now we understand, oh, between N MOSFET and P MOSFET, they have 4 times difference in their maximum current conduction capability. Yes, we know it, but why? Why we have such kind of a strange thing? So please note that this inverter, this sizing is try to match the unit inverter. So in our unit inverter, how does it look like? So in this case we have 1 and relative 2, and when we consider, for example, pull down network, so falling edge, in this case what will be the current flowing through in this way? Of course, here we have no contribution from turned off P P MOSFET doesn't play any role. And in this case, we have just a unit-sized N MOSFET, so its current try to pull down this output voltage is simply given by the unit value I. Then now let's come back to our current design. So in this case, no, our P MOSFET is not turned off when we have a falling edge. So even in this falling edge, previously for this CMOS implementation, this one does not contribute at all. However, now our P MOSFET still try to charge, not discharge, charge this output point, output node with the current of 1/3 I. And now this N MOSFET is also try to discharge in this current. So that's the reason why we say that there is some tendency to charge it and there is some tendency to discharge it. So the net discharging strength felt by this output node is simply given by the difference between them. So from this consideration, we say that the I is the one felt by our N MOSFET. That's the reason why we have selected seemingly quite a strange way or ratio for our N MOSFET and P MOSFET. And now let's say that, okay, so now it has the same driving current for discharging phase. Then let's try to calculate the logical effort and parasitic delay. So when we have the same driving current, then first we can try to find out the input capacitance. So in this case, in our CMOS implementation, so static CMOS implementation, the input just connected to both of our N MOSFET and P MOSFET. So we expect the input capacitance of 3 times unit value C. Then please try to estimate the input capacitance seen from this A node. Seen from A node, actually this P MOSFET doesn't play any role because it is not connected to the A. So what we can see from this A node is just 4/3 of C. Are you with me? So although the size of our N MOSFET is slightly wider, but we can completely kick out the contribution from our P MOSFET. So the overall input capacitance is much smaller than our usual CMOS inverter when we take this kind of ratio. Then we can easily understand. Here we have so 4/9 as a logical effort for this down or falling edge. So of course this is for falling edge. However, for rising edge, the situation becomes a little bit different because in the case of our charging case, now we don't have this A at all, so we have just a simple this one. So it is corresponding to the driving force or charging current of 1/3 I. So the comparison should be made not this unit-sized one, but which has just much smaller one. So therefore, in this case, however, still our input capacitance is given by just 3 times 4C. Yes, because A is still connected to this inverter. However, now what happens? The input capacitance seen from this uh, not unit inverter, 1/3 sized inverter is given by just C. So you can see that the logical effort in the case of rising edge is unfortunately 3 times higher than that of falling edge. So you know that this is once again we are now experiencing there is no um, free meal in this world. If you get something in your falling edge, then that is related with another cost for your rising edge. That is seen from this one. Okay, so now let's go to other ones. So now we can make some general comments taken from our textbook. This kind of circuit family is called as ratioed circuit. The reason why that is called as ratioed circuit is in case of our CMOS implementation. So actually, whether we have a certain ratio N and P doesn't make big difference in its logic values. Of course, what we can say is V out and V in. If we introduce once again this voltage transfer curve, everybody understand if we have a much wider P MOSFET, then since pull up network is much powerful than that one, so we will have this kind of behavior, highly skewed to the high value. And also if we have the opposite case, if N MOSFET is much wider than P MOSFET, then we will have this behavior. Yes, of course, both of them are not that much ideal. However, it is certain that if you give 0, then it will give you VDD. If you give VDD, then it will give you 0. At least these two logic values are not affected by this ratio. What is the size of your N MOSFET and what is the size of your P MOSFET? That does not make any difference in your logic level. However, unfortunately, in this ratioed gates, depending on the size of your P relative size of your P MOSFET, actually the logic level itself that is affected by that ratio. So that's the reason why this kind of circuits or logic gates are called as ratioed logic gates. So in this case, they reduce the input capacitance. How did we kick out the input capacitance? Because in this A input signal, it is not connected to the P MOSFET. So although P MOSFET is there, however, it is not contributing the input capacitance. Yes, that's good, but slow rising transition. We have seen it before. And DC power consumption. Yes, so here that is they are related in this way. And also output level, when we have certain high voltage, then in this case we can have non-zero values for input high value. That is not good for our application. So we quickly move to the other one. So simply speaking, this PMOS or pseudo NMOS implementation can be regarded as just another version of our NMOS only technology, but that is not that good in terms of many cases. I think that most of our lecture will be devoted to this second family, the dynamic gate. So in this dynamic gate, we have much more things to be covered. Um, what we can expect is, okay, we wanted to kick out this PMOSFET. So in order to kick out this PMOSFET, we have just to try to avoid it from its input line. However, due to the static gate voltage of this PMOSFET, always it has some current. So the next idea, instead of this pseudo NMOS implementation, is the dynamic one. The dynamic one is also separate this PMOS out of this input one. Still, we have an additional signal which is not directly related to A value. So when we consider A value, still we don't have any contribution from P MOSFET. Good. But point is, one of the significant difficult was, yes, this one. When we have the falling transition, now that is determined by this MOSFET, even in this case, our 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 PMOSFET had it or is which has the gate voltage grounded, always try to conduct something. So what happens if we just shut down the P MOSFET for falling transition? That is the basic idea of this dynamic gate. So simply speaking, we have one phase. Using this clock signal, first prepare our Y value to 0. Oh, sorry about that, not 0. 1. First charge it. After that, this clock signal becomes 2 VDD. Then now this PMOSFET is completely shut down. After that, only with this input signal A, then A determines whether Y should be discharged or just kept as logical 1. So from the viewpoint of A, so when A signal comes in, it sees that there is something already charged capacitor, charged node Y. Then it says that it is your sole decision, your MOSFET's sole decision whether that should be discharged or not discharged. So using only N MOSFET, please try whether you will discharge it or not. That is the main philosophy of our dynamic circuit. Then, so from the viewpoint of this A, it just see N MOSFET part, so it has some advantages of pseudo N MOSFET implementation. Good. Also, at the same time, since the clock signal becomes 1 for this discharging phase, so there is no contribution from our PMOSFET. PMOSFET never conduct during this discharging phase or output falling transition. So that is the main idea of our dynamic gate. So I have told you that first we must prepare y value, y node to 1, and after that our NMOS only circuitry should pull down network should determine the logical value. Therefore, we must introduce two different phases or modes. One is called as free charge and pre-charge, and another one is evaluate. So in the case of pre-charge mode, we just prepare y equal to 1, and the other one is simply given by just evaluating. In the case of evaluating, we have to apply the clock signal equal to 1, so clock signal high, then this P MOSFET is turned off, and this discharging is solely determined by this N MOSFET pull down network. So are you with me? If you cannot understand my explanation, then please let me know. I will try to deliver this message once again. Okay, so if you don't have any question, then let's go to this way. One thing we have to be careful is in the pre-charge case. In the case of a pre-charge, we try to make y the output equal to 1. So in this case, so let's come back to our previous case. In this case, in pre-charge case, we just apply 0 value for our clock signal. Okay, now its gate voltage is 0, and P MOSFET is now trying to charge it. But for example, if we have a signal equal to logical value 1, then what will happen? Actually, in this case, P MOSFET is turned on, and also, unfortunately, also our N MOSFET is turned on, and they will, both of them will try to conduct current. So from VDD to ground, there will be another current conduction path. Well, that is not that much desirable, because the main reason why we introduced this clocked signal for our P MOSFET was to avoid this current. So therefore, in order to prevent this unwanted case, sometimes we can also additionally include another N MOSFET, not P MOSFET, but N MOSFET. When we have this N MOSFET and it is shared by also same clock signal, then think about the pre-charge case. In order to make a pre-charge, then we have to apply logical value 0. Then our P MOSFET is turned on, and it tries to charge our Y node. At the same time, since clocked signal is 0, our put N MOSFET is turned off. So regardless the value of your input signal A, this pull down network is just shut down. So you don't have any current flowing through the pull down network. So your pre-charge phase or pre-charge mode can be quite safe. Okay, so this is put it implementation. So when we have pre-charge case 0, then this one is on and this one is off, so it is not gone. Of course, when we go to the evaluation phase, then still we have a desirable signal because now this P MOSFET is turned off and our put device still gives you completely on characteristics and it does not affect the logical behavior of our pull-down network. So everything looks quite good, but of course you understand compared with this on-put implementation, we must introduce additional N MOSFET. Always it is not that good in terms of size or something, so that should be also understood.
저기서 푸티드 이제 엠모스를 갈때
Okay.
그 이제 프리차지 스테이지에서 커런트가 풀다운 네트워크로 흐르는 거를 막기 위해서 이제 푸티드 엠모스가
Yes,
달리는
you're right.
건데
Yeah.
근데 결국엔 저희 푸티드 엠모스 드레인 소스 드레인 쪽에
You know this point?
네, 캡이 어쨌든 여기서는 표현이 안 됐지만 캡이 있다고 볼 수
Yeah,
있잖아요.
sure.
그럼 결국엔 또 거기로 패스가 생겨서 저희가 흘러버리는 거예요.
Oh, no. If you have, okay, so since we have also foreign students, I want to repeat his question again. So please comment if I have misunderstood your question. His question is like this. Okay, here we have a put it one, and unfortunately here we have an additional diffusion cap here. So his question was the possibility of a current conduction through this capacitance. However, in this case, we don't consider the current conduction through the diffusion capacitance because even if we are talking about this high-speed logic, but current conduction is assumed as only through this resistive path. This capacitance is just considered as the places for storing the charge. So simply speaking, but still it is true. Yes, if we have this node, additional node, and that will contribute to additional capacitance. That is true. So therefore, compared with this on-put implementation, it contributes additional load capacitance that should be charged and discharged. So in terms of this logical effort, that is not that good, but yes, please, we don't consider the current conduction like this one. Of course, if we have, but you are in some sense, if we have some charge collected in this node, then that should be discharged through this input or outputted and MOSFET. Also, that should be charged and discharged. In that sense, this existence of this putted and MOSFET is not that good for your speed consideration. But if you don't have it, then it has some side effect of increase of DC power or not this power, even not this power, but here we have a contention current in the falling transition or in our sense pre-charge phase, so that is unavoidable for some cases. Of course, I wanted to say that if we have some certain case where input is always, or this net pull down network always shut down, then we don't have to include this put MOSFET. So sometimes we can find certain conditions to neglect this put MOSFET, but when we don't have such kind of a certification or certain condition, then it is better to include this one. That was a really good question. And here I have just taken this table out of our textbook and made some comparison between the red colored quantities. What is the red colored quantities? They are the logical effort and propagation delay for static CMOS implementation. Please make a comparison between the CMOS, static CMOS and our implementation. So dynamic circuit implementation. So yes, in the case of our inverter, it is smaller, and in our NAND gate also it is smaller. And however, you know that the biggest advantages can be found here in the case of NOR. So anyway, in every cases we get some, even with this put it one, we get certain advantages in terms of logical effort and propagation delay. So if you are interested, then please try to calculate it. So simply speaking, starting from our pseudo MOSFET, which you always try to charge our output node, it is certain advantages because the charging phase is just limited by our clock signal. So we just prepare fully charged output and only input signal discharge it. Oh, sounds great, but there is one problem. Since this is always assumed that here we have a certain already charged value and discharging is determined by A, so allowed behavior is okay, it was 1, but A makes discharge, so it can be 1, or discharge, so it can be 0, or it is not discharged at all, so it is just kept as 1. However, transition from 1 to 0, so it is not for, please note that it is not for your output, but they are transition for our input. So now think about this one. This is a signal, this is the input signal, and please note that this notation for your input signal. And now let's assume that in this evaluation phase, our input signal is changed from its logical value 1 to 0. Of course, since it is just an inverter, what we can expect is, since input is changed from 1 to 0, output will be changed from 0 to 1. However, since A was 1, so in this evaluation phase, already your output was fully discharged. Then after that, inside this evaluation phase, when we have 0 to 1 transition for our input, then although we must have this rising edge or rising transition for our output, unfortunately this PMOSFET in this evaluation phase is completely turned off. There is no driving force to fill or charge the capacitor once again. So the answer is, even though we have applied this 1 to 0 transition for our input, but our output does not react to that input transition. So what we have in reality is just nothing. Then you know that this is just regarded as a failure of your logic operation. So please consider this one. Um, Here, when you have one dynamic logic, so now let's say that this is just an inverter, and here once again you have a dynamic inverter. You have two inverters. So what you wanted to get is, since A is 1, so x becomes just logical 0, and after that y becomes 1. But what will happen to your output? Y. So it is not that easy to get 1 using this one. So now think about this one. Pre-charge phase, your x value, y value is just given by your clock signal. Your clock signal 0 just to fill your x and your y. So they are all 1. And now, in the case of evaluation phase, now your P MOSFET doesn't play any role. Okay, they are gone. And now, since your A is always 1, so since it is always 1, now your X is discharged. So this is exactly the one from 0 to, sorry about that, 1 to 0 transition. So if we have 1 to 0 transition for our second stage, so what will happen? So now your y value is 0, and since your x now becomes 0, in this case you don't okay, since that is 0, this one in this phase here we have still discharge phase. So although if this is really inverter and inverter serially connected, what you wanted to get is it is just kept as 1 because that is just a buffer, but in this case it is also discharged in that way. Please try to draw it and you will find that this is a failure of your logical operation. So simply speaking, dynamic gate wanted to have only this kind of operation, but unfortunately your dynamic circuit always generates such kind of input. So serially connected dynamic gates cannot be used properly for your logic system. So instead of that, what they do is, okay, serially connecting dynamic circuit to dynamic circuit is not that much suitable. So instead of that, just to insert static inverter here and static inverter here. So the configuration is dynamic logic gate and static one, and dynamic logic gate and static one. So now think about this one. Dynamic logic gate always monotonically monotonically falling out. So it generates monotonically falling output signal. However, this static inverter always converts it to rising one. So from the viewpoint of this second dynamic gate, the input is always rising. After that, now it generates also falling signal. However, that is recovered by this CMOS inverter once again as a Elijah one. So therefore, by using this so-called domino gate, then we can always keep the property of monotonically rising input signal. So then we can make some chain of logic gates. So now this is called as domino gate. It is because it's like this. Let's think about a kid who plays the domino game. Then he or she should prepare the domino. There are many domino bricks, and he or she should place them in a determined way. That can be just analyzed as this pre-charge phase. Once after all of their setting is over, then what happens? The very first domino brick is just touched. After that, the signal is just propagate all over the logic gate. That is just quite similar between this evaluation phase. So just setting the bricks, that is related with setting your all y values to 1. That is corresponding to the pre-charge phase. After that, once the very first signal comes in, after that, just like a domino play or domino game, your logic values are evaluated. So that's the reason why we call it as domino gate. So please note that pre-charge. So when you pre-charge it, then each of your P MOSFET here and there. Here we have just two-stage domino gate, and in order to set your Y value and W value, actually your P MOSFET and P MOSFET works in parallel. So you don't have to make a serial consideration. So you can just within this pre-charge phase, only a P MOSFET can charge a single output node. That is enough. However, in the case of this evaluation phase, what happens? The signal this one comes here and there, and y affects x affects y, and y affects z. So within given time period, your evaluation should be done. So simply speaking, which one is more critical in terms of operational speed? Of course, your evaluation part is much more critical for given time period. Your pre-charge can be much slower because you have sufficient margin or time duration to pre-charge your individual output node. So therefore, evaluation is really critical in this case. However, pre-charge is not that much critical, so therefore you can use a relatively small P MOSFET to charge it. Although the original domino logic has the dynamic something, so not only dynamic NAND, but we can have a dynamic something and a static inverter. However, sometimes instead of that, we can use any kinds of other logic static logic gate which have inverting property. For example, at the first glance it looks quite complicated. Then please think about the operation of this one. In the pre-charge phase, then here we have a node. This node will be charged to 1, and also here we have the value charged to 1, and we have 8 different select signal, and it is assumed that among 8 of them, only one of them is actually 1, and all other becomes just 0. For example, let's assume that we select this second signal. Then what will happen? In this evaluation phase, now P MOSFET is gone and P MOSFET is gone, and also all other S signals are 0. So our pull down network, this pull down network, all of pull down networks which have just S signal of 0 will not contribute to this discharging phase. Okay, so now let's say that S2 equal to 1. Then, depending on your D2, if your D2 equal to 1, then your output, this node value will become 0. And if your D2 value equal to 0, then still you will have this output value. So you know this is 1, and you have a bubble and you have 0. So since this is just an OR gate, so it doesn't play any role. So therefore, depending on this value, when this output value is 1, your Y value become 1, and your Y value become 0. Oh, sorry, what? Oh, yes. Yes, you're right. So now you can see that if we have S2 equal to 1, when S2 is selected, so D2 is selected, your output value Y will be the same with your D2, and your Y will be also same to D2. So simply speaking, you have your Y equal to D2 when S2 equal to 1. What is this? You select a certain input signal, and your output signal is the data of that index. This is nothing but a multiplex. So this is just 8 input multiplexer generated or implemented with dynamic circuit and inverting one, but this is not inverter. This is, what is this? This is NOR gate. Oh, sorry about that. Not NOR. This is NAND gate. So this is not the original domino logic, but this one is called as compound domino logic. And why do we study this one? Of course, multiplexer is quite important for our digital system, and this kind of implementation, so come with the implementation with the compound domino logic, have certain advantages in terms of its speed. So that's the reason why we have studied this one. So another topic for our dynamic logic is keeper. Here we have keeper. So For example, pre-charge phase, we pre-charge, so y equal to 1. We know it. After that, evaluation, our basic assumption is only pull-down network can discharge our y value to y equal to 0. There is only one single mechanism. So it's like this. Here we have already fully charged one and pull down network. That is the way to discharge our output value. This is Y node. However, since transistors are leaky, even when we have a pull down network is seemingly completely turned off. Then if everything is really ideal, then even after a long time later, the value of your Y node should be still node 1. But unfortunately, how did we generate this pull down network? It is just serially or parallelly connected N MOSFET, and N MOSFET has many different leakage sources. So if we have, for example, junction leakage, so then through that way, or even not only junction leakage, I mean that here if we have this output node, here we have output node, then we can have a direct path from drain to ground, and also another path is sub-threshold leakage current, and also we can have many different ways to discharge it. So transistors are leaky, and if we wait too long, then actually even though for example, even though when a equal to 0, so although this one does not play at all, however the output value will be diminished. For example, think about this one. Now we have 1 well prepared as 1, and now logical value is 0, so ideally it should be 0. However, in this evaluation phase phi, this clock signal is 1, so this one is now ready to conduct. So the leakage current is simply given by the leakage current of our A transistor, and if A transistor that is leaky, then this leakage current will flow through this chain. So after some time later, our Y value, V of not Y is here located here, so not Y, but anyway, this node value, this value will be decreased from VDD minus times certain resistance shown here. Yes. So let's say that this one will be smaller than Y value or VDD value. So in order to prevent this problem, here we introduce a simple trick. Say that this is 1, then if we have this notation, then what will happen? Here we have Y value equal to 0. Then if this is 0, then this 0 is feedback to our weak transistor. Please note that this transistor is quite weak, and this weak transistor is turned on. So if our signal is just slightly diminishing, then this one will be just recharged by our keeper PMOS. Then you may say that, oh, it sounds a little bit strange. in this evaluation phase, for example, if we have just discharging, wanted discharging, for example, say that 1, then this node voltage should be immediately go to 0. Then what happens? If we have such case, if we did this go to 0, then this 0 is inverted to 1 and this 1 is fed back to our PMOSFET. What happens? In this case, nothing happens. Our PMOSFET does not play any role. However, if we have just a slight decrease of our values from 1, then it even with this inverter operation it will still 0, so it is just recharged like this one. But it is still true that this PMOSFET should be small. I mean that not small but narrow, so it should be weak. Otherwise, some cases this pull-down network and weaker can have some competition to charge or discharge this circuit. Okay, although we have the last slide for pass transistor circuits, but that is not that much practical in these days, so just to have a look at this one. Here we have a 2-input multiplexer, and A is then when S equal to 1, then this MOSFET is turned on and this PMOSFET is turned on. Also, when S equal to 1 at the same time, this PMOSFET is turned off and this MOSFET is turned off. So therefore, we have a strong coupling between A and this node. This one becomes just a copied value of A, and that is inverted, so we will have A bar here. So that is 2-input multiplexer. The contents of our textbook is, okay, it has both of NMOSFET and PMOSFET. Also here we have NMOSFET and PMOSFET, and we don't like PMOSFET. So the idea is, why don't we kick out this PMOSFET and PMOSFET? Then can we still have a certain logic gate without PMOSFET? Yes, there have been many different suggestions, but that they are not being used in practice, so I don't want to keep this discussion any further. Okay, so simply speaking, today's main topic was dynamic logic gates. So it tried to pre-charge and evaluate. So since that is given as pre-charge and evaluate, it prefers to have some transitions. For example, where can you find it? Yes, it has some preference for input signal, but this is not possible because this one dictates just charging again. However, we have no ability to charge this output node during this evaluation phase. So therefore, single dynamic gates cannot be serially connected in at least in a single evaluation phase. So if we do multiple logic operation in a single clock period, then we have to introduce this kind of domino implementation in order to keep the monotonicity of our input signal. So that was the main lesson out of our today's talk. However, once again, although we have spent completely 1 lecture hour to all of these implementation, but the most important one we wanted to say is static CMOS is the king of the logic implementation, and whenever possible, then we must use a static CMOS, and the main reason is its robustness. Yes, so since it is robust as a designer, you must use static CMOS as much as possible. Okay, so although not that much detailed, but I think that that will be the day for combinational circuit design, and we have only 2 remaining lectures. Our second last lecture will be devoted to the sequential circuit, quite a brief discussion about sequential circuit, and the last lecture is reserved for SRAM. Although I think that in many cases SRAM is not importantly considered in this course, but since SRAM is quite an important component of a digital system, I wanted to make the last lecture for SRAM. Okay. Okay. Then, do you have any question? If not, I want to wrap up today's lecture. Thank you for your attention.